Okay, this lecture is mostly about the idea of similar matrices. I'm going to tell you what that word similar means and in what way two matrices are called similar. But before I do that, I have a little more to say about positive definite matrices. You can tell this is a subject I think is really important, and I told you what positive definite meant. It means that this expression, this quadratic form, x transpose AX, is always positive. But the direct way to test it was with eigenvalues or pivots or determinants. So we know what it means, we know how to test it, but I didn't really say where positive definite matrices come from. And so one thing I want to say is that they come from least squares. And all sorts of physical problems start with a rectangular matrix. You remember in least squares the crucial combination was A transpose A. So I want to show that that's a positive definite matrix. So I'm going to speak a little more about positive definite matrices, just recapping. Let me ask a question. It may be on the homework. Suppose a matrix A is positive definite. I mean by that, I'm assuming it's symmetric. That's always built into the definition. So we have a symmetric positive definite matrix. What about its inverse? Is the inverse of a symmetric positive definite matrix also symmetric positive definite? So you quickly think, okay, what do I know about the pivots of the inverse matrix? Not much. What do I know about the eigenvalues of the inverse matrix? Everything, right? The eigenvalues of the inverse are 1 over the eigenvalues of the matrix. So if my matrix starts out positive definite, then right away I know that its inverse is positive definite, because those positive eigenvalues, then 1 over the eigenvalue is also positive. What if I know that a matrix A and a matrix B are both positive definite? Let me ask you this. Suppose if A and B are positive definite, what about A plus B? In some way, you hope that that would be true. It's positive definite for a matrix is kind of like positive for a real number. But we don't know the eigenvalues of A plus B. We don't know the pivots of A plus B. So we just have to go down this list of, all right, which approach to positive definite can we get a handle on? And this is a good one. This is a good one. How would we decide that if A was like this and if B was like this, then we would look at X transpose A plus BX. I'm sure this is in the homework. Now, so we have X transpose AX bigger than 0, X transpose BX positive for all X. So now I ask you about this guy. And of course, you just add that, and we get what we want. If A and B are positive definite, so is A plus B. So that's what I've shown. So is A plus B. Just be sort of ready for all the approaches through eigenvalues and through this expression. And now, finally, one more thought about positive definite is this combination that came up in least squares. Can I do that? So now suppose A is rectangular, m by n. So I'm sorry that I've used the same letter A for the positive definite matrices and the eigenvalue chapter that I used way back in earlier chapters when the matrix was rectangular. Now, that matrix, a rectangular matrix, no way it's positive definite. It's not symmetric. It's not even square in general. But you remember that the key for these rectangular ones was A transpose A. That's square. That's symmetric. Those are things we knew. We knew back when we met this thing in the least squares stuff, in the projection stuff. But now we know something more. We can ask a more important question, a deeper question. Is it positive definite? And we sort of hope so. Like we might, in analogy with numbers, this is like sort of like the square of a number, and that's positive. So now I want to ask the matrix question. Is A transpose A positive definite? Okay, now so again, it's a rectangular A that I'm starting with, but it's the combination A transpose A that's the square, symmetric, and hopefully positive definite matrix. So how do I see that it is positive definite, or at least positive semi-definite? You'll see that. Well, I don't know the eigenvalues of this product. I don't want to work with the pivots. The right quantity to look at is this: X transpose AX. X transpose times my matrix times X. I'd like to see that that expression is always positive. I'm not doing it with numbers, I'm doing it with symbols. Do you see, how do I see that expression comes out positive? I'm taking a rectangular matrix A and an A transpose. That gives me something square symmetric, but now I want to see that if I multiply, that if I do this, I form this quadratic expression, that I get this positive thing that goes upwards when I graph it. How do I see that that's positive? Or absolutely, it isn't negative anyway. We will have to spend a minute on the question, could it be zero? But it can't be negative. Why can this never be negative? The argument is like the one key idea in so many steps in linear algebra. Put those parentheses in a good way. Put the parentheses around AX, and what's the first part? What's this X transpose A transpose? That is AX transpose. So what do we have? We have the length squared of AX. We have, that's the column vector AX, that's the row vector AX. It's length squared, certainly greater than or possibly equal to 0. So we have to deal with this little possibility. Could it be equal? Well, when could the length squared be 0? Only if the vector is 0, right? That's the only vector that has length squared 0. So I would like to get that possibility out of there. So I want to have AX never be 0, except, of course, for the 0 vector. How do I assure that AX is never 0? In other words, how do I assure that there's no null space of A? The rank should be, so now remember, what's the rank when there's no null space? By no null space, you know what I mean. Only the 0 vector in the null space. So if I have an 11 by 5 matrix, so it's got 11 rows, 5 columns, when is there no null space? So the columns should be independent. What's the rank? N 5. Rank n. Independent columns. Then I conclude, yes, positive definite. And this was the assumption that then A transpose A is invertible. The least squares equations all work fine. And more than that, the matrix is even positive definite. And I just to say one comment about numerical things. With a positive definite matrix, you never have to do row exchanges. You never run into unsuitably small numbers or zeros in the pivot position. They're the great matrices to compute with, and they're the great matrices to study. So that's, I wanted to take this first 10 minutes grab the first 10 minutes away from similar matrices and continue this much more with positive definite. I'm really at this point now coming close to the end of the heart of linear algebra. Positive definiteness brought everything together. Similar matrices, which is coming the rest of this hour, is a key topic. And please come on Monday. Monday is about what's called the SVD, singular values. It's has become a central fact in a central part of linear algebra. I mean, you could come after Monday also, but Monday is that singular value thing has made it into this course. 10 years ago, 5 years ago, it wasn't in the course. Now it has to be. Okay, so can I begin today's lecture proper with this idea of similar matrices? This is what similar matrices mean. So here, let's start again. I'll write it again. So A and B are similar. A and B are, now these matrices, I'm no longer talking about symmetric matrices. At least no longer expecting symmetric matrices. I'm talking about two square matrices, n by n. A and B, they're n by n matrices. And I'm introducing this word similar. So I'm going to say, what does it mean? It means that they're connected in the way, well, in the way I've written here, so let me rewrite it. That means that for some matrix M, which has to be invertible, because you'll see that, this one matrix is, take the other matrix, multiply on the right by M, and on the left by M inverse. So the question is, why that combination? What part of the answer you know already? You remember we've done this. We've taken a matrix A. So let's do an example of similar. Suppose A, the matrix A, suppose it has a full set of eigenvectors. They go in this eigenvector matrix S. Then what was the main point of the main calculation of the whole chapter is use that eigenvector matrix S, and its inverse comes over there to produce the nicest possible matrix, lambda. Nicest possible because it's diagonal. So in our new language, this is saying A is similar to lambda. A is similar to lambda because there is a matrix, and there is an M, and this particular M is this important guy, this eigenvector matrix. But if I take a different matrix, M, and I look at M inverse AM, the result won't come out diagonal, but it'll come out a matrix B that's similar to A. Do you see that what I'm doing is like I'm putting these matrices into families. All the matrices in the family are similar to each other. Each one in this family is connected to each other one by some matrix M, and like the outstanding member of the family is the diagonal guy. I mean, that's the simplest, neatest matrix in this family of all the matrices that are similar to A. The best one is lambda. But there are lots of others, because I can take different, instead of S, I can take any old matrix, M, any old invertible matrix, and do it. I better do an example. Okay. Suppose I take A as the matrix 2, 1, 1, 2. Okay. Do you know the eigenvalue matrix for that? The eigenvalues of that matrix are, well, 3 and 1. So that, and the eigenvectors would be easy to find. So this matrix is similar to this one. But my point is, I can also take my matrix 2, 1, 1, 2. I could multiply it by, let's see, I'm just going to cook up a matrix M here. Let me just invent 1, 4, 1, 0. And over here I'll put M inverse. And because I happen to make that triangular, I know that its inverse is that. Right? So there's M inverse AM. That's going to produce some matrix. Oh, well, I got to do the multiplication. So hang on a second. I'll just copy that 1 minus 4, 0, 1 and multiply these guys. So I'm getting 2, 9, 1, and 6, I think. Can you check it as I go? Because you see, I'm just... So that's 2 minus 4. I'm getting a minus 2. 9 minus 24 is a minus 15. My God, how did I get this? And that's probably 1 and 6. So there's my matrix B. And there's my matrix lambda. There's my matrix A. And my point is, these are all similar matrices. They all have something in common, besides being just 2 by 2. They have something in common. And what is it? What's the point about two matrices that are built out of, the B is built out of M inverse AM? What is it that A and B have in common? That's the main, now I'm telling you the main fact about similar matrices. They have the same eigenvalues. This chapter is about eigenvalues, and that's why we're interested in this family of matrices that have the same eigenvalues. What are the eigenvalues in this example? Lambda. The eigenvalues of that I could compute. The eigenvalues of that I can compute really fast. So the eigenvalues are 3 and 1. For this, for sure. Now, did you see why the eigenvalues are 3 and 1 for that one? If I tell you the eigenvalues are 3 and 1, you quickly process the trace, which is then 4, agrees with 4, and you process the determinant, 3 times 1. The determinant is 3, and you say, yes, it's right. Now, I am hoping that the eigenvalues of this thing are 3 and 1. May I process the trace and the determinant for that one? What's the trace here? The trace of this matrix is 4, minus 2 and 6, and that's what it should be. What's the determinant? Minus 12 plus 15 is 3. The determinant is 3. The eigenvalues of that matrix are also 3 and 1. And you see, I created this matrix just like I just took any m, like one that popped into my head, and computed M inverse AM. Got that matrix. It didn't look anything special, but it's like A itself. It has those eigenvalues 3 and 1. So that's the main fact, and let me write it down. Similar matrices have the same eigenvalues. So I'll just put that as an important point. And think why. Why is that? So that's what that family of matrices is. The matrices that are similar to this A here are all the matrices with eigenvalues 3 and 1. Every matrix with eigenvalues 3 and 1, there's some m that connects this guy to the one you think of. And then, of course, the most special guy in the whole family is the diagonal one with eigenvalues 3 and 1 sitting there on the diagonal. But also, I could find, tell me just a couple more members of the family. Tell me another matrix that has eigenvalues 3 and 1. Well, let's see. I'll just make it triangular. That's in the family. There is some m that connects to this one. And also this. There's some matrix M so that M inverse AM comes out to be that. There's a whole family here. And they all share the same eigenvalues. So why is that? Okay. I'm going to start, the only possibility is to start with AX equal lambda x. Okay, so suppose A has the eigenvalue lambda. Now I want to get B in the picture here somehow. Remember, B is M inverse AM. Let's just remember that over here. B is M inverse AM. And I want to see its eigenvalues. How am I going to get M inverse AM into this equation? Let me just sort of do it. I'll put an M times an M inverse in there. Right? I haven't changed the left-hand side, so I better not change the right-hand side. So everybody's okay so far. I just put an M. See, I want to get it. So now I'll multiply on the left by M inverse. I have to do the same to this side. And that number, lambda, is just a number, so it factors out in the front. So what I had here is this was safe. I did the same thing to both sides. And now I've got B. There's B. That's B times this vector M inverse x is equal to lambda times this vector M inverse x. So what have I learned? I've learned that B times some vector is lambda times that vector. I've learned that lambda is an eigenvalue of B also. So this is if lambda is an eigenvalue of A, then I can write it this way, and I discover that lambda is an eigenvalue of B. That's the end of the proof. The eigenvector didn't stay the same. Of course, I don't expect the eigenvectors to stay the same. If all the eigenvalues are the same and all the eigenvectors are the same, then probably the matrix is the same. Here, the eigenvector changes. So the eigenvector, so the point is then the eigenvector of B is M inverse times the eigenvector of A. Okay. That's all that this says here. The eigenvector of A was x, and so the M inverse. similar matrices, then, have the same eigenvalues and their eigenvectors are just moved around. Of course, that's what happened way back in the most important similar matrices are to diagonalize. So what was the point when we diagonalized? The eigenvalues stayed the same, of course, 3 and 1. What about the eigenvectors? The eigenvectors were whatever they were for the matrix A, but then what were the eigenvectors for the diagonal matrix? They're just, what are the eigenvectors of a diagonal matrix? They're just 1, 0, and 0, 1. So this step made the eigenvectors nice, didn't change the eigenvalues, and every time we don't change the eigenvalues, same eigenvalues. Okay. Now, so I've got all these matrices, I've got this family of matrices with eigenvalues 3 and 1. Fine. That's a nice family. It's nice because those two eigenvalues are different. I now have to get into the less happy possibility that the two eigenvalues could be the same. And then it's a little trickier, because you remember, when two eigenvalues are the same, what's the bad possibility? That there might not be a full set of eigenvectors, and we might not be able to diagonalize. So I need to discuss the bad case. So the bad, can I just say bad? If lambda 1 equals lambda 2, then the matrix might not be diagonalizable. Suppose lambda 1 equals lambda 2 equals 4, say. Now, if I look at the family of matrices with eigenvalues 4 and 4, well, one possibility occurs to me. One family with eigenvalues 4 and 4 has this matrix in it, 4 times the identity. Then another, but now I want to ask also about the matrix 4, 4, 1, 0. And my point, here's the whole point of this bad stuff, is that this guy is not in the same family with that one. The family of matrices that have eigenvalues 4 and 4 is 2 families. There's this total loner here who's in a family off, right, just by himself. And all the others are in with this guy. So the big family includes this one. And it includes a whole lot of other matrices. All, in fact, in this 2 by 2 case, you see what do I mean? What am I using this word family? In a family, I mean they're similar. So my point is that the only matrix that's similar to this is itself. The only matrix that's similar to 4 times the identity is 4 times the identity. It's off by itself. Why is that? If this is my matrix, 4 times the identity, and I take it, I multiply on the right by any matrix M, I multiply on the left by M inverse, what do I get? This is any M, but what's the result? Well, factoring out a 4, that's just the identity matrix in there. So then the M inverse cancels the M. So I've just got this matrix back again. So whatever the M is, I'm not getting any more members of the family. So this is one small family, because it only has one person. One matrix. Excuse me, I think of these matrices as people by this point in 1806. Okay, the other family includes all other matrices that have eigenvalues 4 and 4. This is somehow the best one in that family. See, I can't make it diagonal. If it's diagonal, it's this one. It's in its own, by itself. So I have to think, okay, what's the nearest I can get to diagonal? But it will not be diagonalizable. Do you know that matrix is not diagonalizable? Of course, because if it was diagonalizable, it would be similar to that, which it isn't. The eigenvalues of this are 4 and 4, but what's the catch with that matrix? It's only got one eigenvector. That's a non-diagonalizable matrix, only one eigenvector. And somehow, if I made that 1 into a 10 or into a million, I could find an M. It's in the family. It's similar. But the best guy in this family is this one. And this is called the Jordan. So this guy, Jordan, picked out, so he studied these families of matrices. And in each family, he picked out the nicest, most diagonal one. But not completely diagonal, because there isn't a diagonal matrix in this family. So there's a 1 up there in the Jordan form. Okay. Yeah, I think we've got to see some more matrices in that family. So let's just think of some other matrices whose eigenvalues are 4 and 4, but they're not 4 times the identity. So, and I believe that all the examples we pick up will be similar to each other. And do you see why? So in this topic of similar matrices, the climax is the Jordan form. So it says that every matrix, I'll write down what Jordan discovered. He found the best looking matrix in each family. And that's, then we've covered all matrices, including the non-diagonalizable one. That's the point, that in some way Jordan completed the diagonalization by coming as near as he could, which is his Jordan form. And therefore, if you want to cover all matrices, you've got to get him in the picture. It used to be, when I took 1806, that was the climax of the course, this Jordan form stuff. I think it's not the climax of linear algebra anymore, because it's not easy to find this Jordan form for a general matrix, because it depends on these eigenvalues being exactly the same. You'd have to know exactly the eigenvalues, and you'd have to know exactly the rank, and the slightest change in numbers will change those eigenvalues, change the rank, and therefore the whole thing is numerically not a good thing. But for algebra, it's the right thing to understand this family. So just tell me another matrix, a few more matrices, so more members of the family. Let me put down again what the best one is. Okay. All right, some more matrices. Let's see, what am I looking for? I'm looking for matrices whose trace is what? So if I'm looking for more matrices in the family, they'll all have the same eigenvalues, 4 and 4. So their trace will be 8. So why don't I just take like 5 and 3? I've got the trace right. Now the determinant should be what? 16. So I just fix this up. Shall I put maybe a 1 and a -1 there? Okay, there's a matrix with eigenvalues 4 and 4, because the trace is 8 and the determinant is 16. And I don't think it's diagonalizable. Do you know why it's not diagonalizable? Because if it was diagonalizable, the diagonal form would have to be this. But I can't get to that form because whatever I do with any m inverse and m, I stay with that form. I could never connect those. So I can put down more members. Here's another easy one. I could put the 4 and the 4 and a 17 down there. All these matrices are similar. If I could find an m that would show that that one is similar to that one. And you can see the general picture is I can take any a, and any 8 minus a here, and any, oh, I don't know, whatever you put it, b. Anyway, you can see I can fill this in to make the trace equal 8, the determinant equals 16. I get all that family of matrices, and they're all similar. So we're seeing what eigenvalues do. They're all similar, and they all have only one eigenvector. So if you allow me to add to this picture, they have the same lambdas, and they also have the same number of independent eigenvectors. Because if I get an eigenvector for x, I get one for a, I get one for b also. So, and same number of eigenvectors. But even more than that, I mean, it's not enough just to count eigenvectors. Yeah, let me give you an example why it's not even enough to count eigenvectors. So another example. So here are some matrices. Oh, let me make them 4 by 4. Okay, here's a matrix. I mean, like if you want nightmares, think about matrices like these. So a 1 off the diagonal, say a 1 there. What are the eigenvalues of that matrix? Oh, okay. What are the eigenvalues of that matrix? Please. 4 zeros, right? So we're really getting bad matrices now. So I mean, this is like, Jordan was a good guy, but he had to think about matrices that had like an eigenvalue repeated 4 times. How many eigenvectors does that matrix have? Well, eigenvectors will be, since the eigenvalue is 0, eigenvectors are be in the null space, right? Eigenvectors are got to be ax equals 0x. So what's the dimension of the null space? 2. Somebody said 2. And that's right. Why? Because you ask, what's the rank of that matrix? The rank is obviously 2. The number of independent rows is 2. The number of independent columns is 2. The rank is 2. So the dimension of the null space is 4 minus 2. So it's got 2 eigenvectors. 2 eigenvectors. 2 independent eigenvectors. All right. The dimension of the null space is 2. Now, suppose I change this 0 to a 7. The eigenvalues are all still 0. What about how many eigenvectors? What's the dimension of what's the rank of this matrix now? Still 2, right? So it's okay. And actually, this would be similar to the one that had a 0 in there. But it's not as beautiful. Jordan picked this one. He put 1s. We have a 1 above the diagonal for every missing eigenvector. And here we're missing 2 because we've got 2. So we've got 2 eigenvectors and 2 are missing. Because it's a 4 by 4 matrix. Okay. Now, but I was going to give you this second example. 0, 1, 0, 0. Let me just move the 1. Oh, not there. Off the diagonal, and 0, 0, 0, 0. Okay. So now tell me about this matrix. Its eigenvalues are 4 zeros again. Its rank is 2 again. So it has 2 eigenvectors and 2 missing. But the darn thing is not similar to that one. A count of eigenvectors looks like these could be similar, but they're not. Jordan, see, this is like a little 3 by 3 block and a little 1 by 1 block. And this one is like a 2 by 2 block and a 2 by 2 block. And those blocks are called Jordan blocks. So let me say, what is a Jordan block? J, block number I, has, so a Jordan block has a repeated eigenvalue, lambda I, on the diagonal. Zeros below and ones above. So there's a block with this guy repeated, but it only has one eigenvector. So a Jordan block has one eigenvector only. This one has one eigenvector, this block has one eigenvector, and we get 2. This block has one eigenvector, and that block has one eigenvector, and we get 2. So, but the blocks are different sizes. And that, it turns out, Jordan worked out, then this is not similar to this one. So I'm like giving you the whole story. Well, not the whole story, but the main themes of the story is here's Jordan's theorem. Every square matrix A is similar to a Jordan matrix J. And what's a Jordan matrix J? It's a matrix with these blocks. Jordan block number 1, Jordan block number 2, and so on. And let's say Jordan block number D. And those Jordan blocks look like that. So the eigenvalues are sitting on the diagonal, but we've got some of these ones above the diagonal. We've got the number of, so the number of blocks is the number of eigenvectors. Because we get one eigenvector per block. So if I summarize Jordan's idea, start with any A. If its eigenvalues are distinct, then what's it similar to? This is the good case. If I start with a matrix A and it has different eigenvalues, it's n eigenvalues, none of them are repeated, then that's a diagonalizable matrix. The Jordan block the Jordan matrix is diagonal. It's lambda. So the good case, J is lambda. There are D equals n. There are n eigenvectors, n blocks, diagonal, everything great. But Jordan covered all cases by including these cases of repeated eigenvalues and missing eigenvectors. Okay, that's a description of Jordan. I haven't told you how to compute this thing. And it isn't easy. Whereas the good case is the good case is what 1806 is about. This case is what 1806 was about 20 years ago. So you can see you probably won't have on the final exam the computation of a Jordan matrix for some horrible thing with 4 repeated eigenvalues. I'm not that crazy about the Jordan form. But I'm very positive about positive definite matrices and about the idea that's coming Monday, the singular value decomposition. So I'll see you on Monday, and have a great weekend. Bye.